Let us begin with image number 1. Before we calculate a single number, before we discuss megawatts or kilograms of hydrogen, we must define the system boundary. This is the first and most important engineering decision. In image number 1, you see the complete hydrogen production facility enclosed within a defined boundary. Inside that boundary are the grid connection, the transformer, the rectifier, the electrolyzer stack, the water treatment system, the cooling system, the gas purification system, compression equipment, and auxiliary systems. Everything inside this boundary must be included in the energy balance. If we exclude any of these components, our analysis becomes incomplete. If we analyze only the stack, we obtain stack efficiency. If we analyze the entire boundary shown in image number 1, we obtain plant efficiency. At industrial scale, plant efficiency is the number that determines capital cost, operating cost, and ultimately the levelized cost of hydrogen. So the first step in plant scale energy balance is not mathematical, it is conceptual. We define what counts. Now move to image number 2. Once the boundary is defined, we apply the first law of thermodynamics. Energy in equals energy out plus losses. In this case, the total electrical energy entering the plant boundary is 53.5 megawatts of alternating current power. That 53.5 megawatts must leave the boundary in another form. There are only 3 possibilities. It leaves as chemical energy stored in hydrogen, as thermal energy rejected to the environment, or as conversion losses within electrical and mechanical systems. There's no fourth category. Energy cannot disappear. It can only change form. The arrows in image number 2 represent this conservation principle. Every megawatt entering must be accounted for leaving. If the balance does not close, the design is incorrect. Now proceed to image number 3, which isolates the electrical conversion stage. The electrical grid supplies alternating current. However, PEM electrolyzers require direct current. Therefore, a conversion is unavoidable. Power first enters the transformer, which adjusts voltage to appropriate levels for downstream equipment. The transformer is not the primary source of inefficiency. It ensures voltage compatibility and safe operation. After the transformer, power enters the rectifier. The rectifier performs the AC to DC conversion at an efficiency of 97%. That means 3% of incoming electrical energy is lost during conversion. If the electrolyzer stack requires 50 megawatts of direct current power, then the required AC input to the rectifier is calculated as 50 divided by 0.97, which equals 51.55 megawatts. The difference, 1.55 megawatts, is conversion loss. That 1.55 megawatts appears as heat within the rectifier cabinets. Immediately we see the first system's coupling. Electrical inefficiency becomes thermal load. The plant must now manage this heat. However, the plant contains more than a stack and a rectifier. Return briefly to image number 1 and consider the balance of plant systems. Water treatment pumps, cooling pumps, control systems, instrumentation, and ventilation systems all consume electricity. These auxiliary loads typically represent 3 to 5% of stack power. In this example, we assume approximately 2 megawatts. Therefore, total AC input to the facility becomes 51.55 megawatts required at the rectifier, plus 2 megawatts for auxiliaries, resulting in approximately 53.5 megawatts of total plant electrical demand. This is the true plant level input. Now that we have established the total input, we can examine the energy conversion inside the stack. Move now to image number 4. Inside the electrolyzer stack, the electrochemical reaction splits water into hydrogen and oxygen. According to the reaction, H2O produces H2 plus 1/2 O2. The stack consumes 50 megawatts of direct current power. The specific energy consumption at the stack level is 55 kilowatt hours per kilogram of hydrogen. To calculate hydrogen production rate, we divide 50,000 kilowatts by 55 kilowatt hours per kilogram. The result is 909 kilograms of hydrogen per hour. Over 24 hours, this equals approximately 21.8 tons per day. Hydrogen contains chemical energy. On a higher heating value basis, hydrogen stores 39.4 kilowatt hours per kilogram. Therefore, the chemical energy leaving the plant per hour is 909 kilograms multiplied by 39.4 kilowatt hours per kilogram, which equals 35.8 megawatts of chemical energy. At this point, we must reconcile input and output. Now proceed to image number 5. Total plant electrical input is 53.5 megawatts. Chemical energy stored in hydrogen is 35.8 megawatts. The difference between these two numbers is 17.7 megawatts. That 17.7 megawatts is heat that must be rejected continuously. This is not optional. If heat accumulates, stack temperature rises. As temperature rises, membrane resistance changes, voltage increases, and efficiency declines. Prolonged elevated temperatures accelerate degradation of the polymer electrolyte membrane. Therefore, cooling capacity must match heat generation at steady state. The red arrows in image number 5 represent this continuous thermal rejection requirement. 17 megawatts of heat is comparable to the cooling load of a medium-sized industrial data center. The cooling system must operate continuously at this capacity. Now examine image number 6, which focuses on water consumption at the reaction level. The stoichiometric requirement for electrolysis is 9 kilograms of water per kilogram of hydrogen. At 909 kilograms per hour of hydrogen production, the theoretical water requirement is 909 multiplied by 9, which equals 8.18 cubic meters per hour. That is the minimum required by chemistry. However, practical plant operation requires more water than stoichiometry alone. Water must be purified to high resistivity standards. Reverse osmosis systems reject a fraction of feed water as concentrate. Cooling towers evaporate water to reject heat. Blowdown is required to control mineral concentration. Therefore, real plant water consumption typically ranges between 15 and 25 liters per kilogram of hydrogen. At 21.8 tons per day, this translates to between 327 and 545 cubic meters per day of water consumption. Water infrastructure becomes a critical design parameter. Move to image number 7, where heat rejection and water usage intersect. Heat rejection of 17.7 megawatts using wet cooling results in evaporation. A common engineering approximation is 1.6 liters of water evaporated per kilowatt hour of heat rejected. At 700 kilowatt hours per hour of thermal rejection, evaporation equals approximately 28 cubic meters per hour. Notice that this evaporation rate exceeds stoichiometric reaction water consumption. This reveals a fundamental systems insight. Electrical inefficiency produces heat. Heat requires cooling. Cooling consumes water. Water treatment requires electricity. Electricity increases plant-level specific consumption. Energy and water are directly linked in plant-scale hydrogen production. Now turn to image number 8, which expands the analysis to a 100 megawatt alkaline plant located on a coastal site using seawater. At 52 kilowatt hours per kilogram, hydrogen production equals 1923 kilograms per hour. Stoichiometric water requirement equals 17.3 cubic meters per hour. However, desalination recovery rate is 45%. Therefore, seawater intake required for processed water equals 17.3 divided by 0.45, which equals 38.4 cubic meters per hour. Cooling water demand may add approximately 68.8 cubic meters per hour. Total seawater intake therefore equals 107 cubic meters per hour, or 2,573 cubic meters per day. Brine discharge equals approximately 838 cubic meters per day at elevated salinity levels of 65 to 70 grams per liter. This requires marine diffusers, environmental impact assessment, and regulatory approval. Water sourcing becomes environmental engineering. Finally, move to image number 9, which integrates the entire energy flow. The Sankey diagram shows 53.5 megawatts of AC input, splitting into 35.8 megawatts of hydrogen energy and 17.7 megawatts of heat rejection, with smaller portions attributed to rectifier loss and auxiliary consumption. Plant efficiency on an HHV basis equals 35.8 divided by 53.5, or approximately 67%. Stack level consumption was 55 kilowatt hours per kilogram. Plant level consumption increased to 58.9 kilowatt hours per kilogram. That difference directly affects hydrogen production cost. At an electricity price of $50 per megawatt hour, each additional megawatt of inefficiency costs $50 per hour, or approximately $438,000 per year of continuous. Stepping back from the numbers, the integrated lesson is clear. A hydrogen plant is not merely an electrochemical device. It is an electrical conversion system, a thermodynamic heat management system, a hydraulic water treatment system, and an environmental interface. Every inefficiency becomes heat. Every heat load becomes cooling demand. Every cooling demand becomes water infrastructure. Every water infrastructure requirement becomes capital cost and permitting complexity. At plant scale, energy balances are not academic exercises. They determine feasibility, cost, and resilience. Every megawatt must balance. Every subsystem exists because of the first law. Once the boundary is defined and the flows are quantified, the plant's physical reality becomes visible. Thermodynamics governs everything.